So game theory for beginners. So I will pick up from where Sitabra actually left, where he kind of discussed the grand organization of sciences. So I'm sure that many of you are from different subjects, right? Physics, biology, mathematics, statistics, what else? Chemistry? No. No. Computer science. Okay. Right. So what I will do first is actually in first 10 minutes, I will take a kind of a grand view of the whole scientific enterprise. Let's see how it goes, and see where game theory fits in. Okay, that's what I'm going to do. So Sitabra already mentioned about this one. Probably you might have read also. Okay, very famous article by Nobel laureate Anderson. So I will just read along these lines. So this probably he mentioned already. The constructionist hypothesis breaks down when confronted with the twin difficulties of scale and complexity. The behavior of large and complex aggregates of elementary particles, it turns out, is not to be understood in terms of a simple extrapolation of the properties of a few particles. Instead, at each level of complexity, entirely new properties appear, and the understanding of the new behaviors requires research, which I think is as fundamental in its nature as any other. I think this is kind of what Sitabra said. I would also want you to focus on that second line that after that it's not highlighted. That is, it seems to me that one may array the sciences roughly linearly in a hierarchy according to the idea that elementary entities of science X and so on. So if you think about it, this is what he means. Okay, I mean this you already know that cells, organs, mind, society, they represent different levels of organization. Okay, what probably you might have seen this, but this is also the roughly why we have different scientific disciplines. Okay, so if you think about it, this is how it goes, right? Fundamental particles forms atoms, then form macroscopic objects, macromolecules and proteins, and at some point you have life, cells, tissues, organs, plants, animals, colonies, societies. Okay, so that's roughly the grand structure. And so you see that physics majorly operates at this level. Okay, chemistry and related fields may be along these three, and then biology and related fields here, and then you have ecology, social sciences, economics, psychology, and so on at this spectrum. Okay. So let's think about it. Okay, so one fundamental thing we do in science in general is this one. Okay, at each of these levels, what is the kind of interaction between the entities? Okay, this is one important question. So for example, in physics, I would study, for example, how a classical objects like a ball react to some force, a Newtonian force. Okay, or how, for example, two charges interact with each other, and so on. And physics, this is relatively straightforward and simple, and probably you might have realized that when it comes to higher orders of organization, these questions becomes very difficult. For example, if you want to ask how two amoebas interact or two living beings interact, that's more difficult than, for example, the question of how two electrons interact. Why? Okay, so this is question for you. Why that is so difficult? Anybody? Any volunteers? Yeah.
The behavior of amoeba.
Yes, but why that is difficult? So one way to see is that, I mean, it has a very rich behavior. For example, living beings do not respond like to a force. You know, a classical particle, for example, if you apply the same force, it will react in the same way every time and so on. But living beings or things around this spectrum has more complex behavior. So they react in a completely, they have options to react in different ways and so on. Okay, and the interactions are itself very difficult to characterize, very difficult to quantify. Okay, so that's the second thing I want to focus on. When you go along this spectrum, do you think that the science becomes more quantitative or less quantitative? Less, more, less, right? Are you sure? Yes, less quantitative, right? Maybe there are exceptions, I will talk about that, but in general, will you see that along this spectrum, when you come along to these portions, the sciences become less and less exact in some sense and less quantitative. But that is changing, for example, in the last few decades, thanks to a lot of data available and computational power, thanks to a large extent to computational power and so on. There is one exception here. For example, if you have taken a course in economics, that's full of quantitative. Why? Why? Because in economics you can quantify things. At least in the subject you can quantify things using money, payoff, or whatever. Okay. All right. Okay. So as Sitabra mentioned, and as Anderson put it beautifully, at each level of organization, you will require new kind of tools and new kind of approach to study them and so on. Okay. So where does games fit in? So I would say that what we are going to talk about mostly fits in this one. Well, exclusively fits in this realm, from living beings onwards to all the higher order systems. Okay. Okay. So I said that a fundamental feature is describing interaction between entities, and if you want to simply define games, it is basically the description of this one. Okay. So entities in biological, social, or economic context are often involved in what is known as interactive decision problems. Okay. So I will spend a few minutes, or you should spend a few minutes to realize what this is. Okay. So I will describe a problem, a very simple one faced by hopefully each of you, and then let's see what makes a decision problem and interactive decision problem different. Okay. So all of you are graduate students, or most of you, right? You live in hostels, right? Okay. So so I was told that all the graduate student hostel rooms looks like this. Is that correct? Right? Okay. Okay. So the one of the crises faced by somebody who is living there is actually this one. Okay. Shall I clean the room or not? Okay. Okay. Let's see this problem. If you are living alone, how many of you live in a single room? Anybody? Oh, right. You? Okay. So how do you decide when to clean your room?
When it becomes
That's okay. Right. And only that is the criteria. When you have time and so on. So let's try to write a law for, what is your name? Soha. So maybe your decision to clean your room is actually something like this, right? The perceived benefit of cleaning the room is a function of several things. You said that. I think you said that level of trash in the room, basically, right? So level of trash. What is the spelling? Trash. Then time. Your energy level, your time level, right? I can write a function of this, and then I can say that I will decide to clean the room when what is an appropriate functional form for this? There are mathematicians. Something like neuron behavior. For example, you see that if it exceeds a threshold, personal dependent threshold, then I will clean the room, right? That's a decision problem. But I would say that's a simple decision problem in the sense that you have full control, and if you know that thing, you can decide. There is no other considerations involved. Now let's think about the situation in which there are two people in the room. Okay, I'm sure rest of anybody living with a roommate or you. Okay. Okay, so if you are living with a roommate, then it could be a little bit more nuanced, right? Because it could be you or it could be the other person who is cleaning the room. Okay, so which means that I have, that's an interactive decision problem, because you see that there are two persons and both of them have this option of either clean or do not clean. Okay, so if you have only these two options, then there are four possible outcomes. Okay, two options, there are only four possible outcomes. So O1 is you clean and the other clean. O2 is you can clean and the other don't, and so on. Okay. So there, whatever you do, there are these four possible options, and you might have some preference over some of these over the others. Okay. So what is your preference? Can you tell me which one do you prefer among these four? Oh, you first one. Okay. So what is your name? Anvita. Anvita is a very nice person. She prefers O1, and then can you rank them? Three, okay? So I will put this sign because he prefers O1, 2, 3. You can have similar preferences. 2. And you don't care about 2 and 4 or something like that?
3 and 2 are about.
3 and 2, so this is something like that, and then this one, right? Okay, so that's the preference. Perfectly fine, there is no problem with that. Somebody else might have a completely different preference. You have a complete different preference. What is your preference?
It's almost the same, but three is more than O2.
No, then it's not the same.
Yeah, if it's not
So you prefer O3?
No, O1 first.
Oh,
O1 and then O3.
okay.
Then O3 is more than O2.
Yeah.
It's not the same, that's it.
Like this?
No, O4 is the least. It's less.
Oh, okay. O4 is the least. Okay, so individuals can have to. What is that?
There's O3 only.
Oh, you prefer O3, okay. So Sitavra is O3 and he don't care about all the remaining stuff. Is that? Okay, so I don't want to write out. That's perfect. So imagine living with Sitavra. that's going to be very, very tricky. Huh? Okay, so the point is that you have preferences, but can you achieve them? That's a question, right? I mean, whether you would like to have your preferences materialized depends upon not just you, but on the other person's decision. And this is the essential of games, for example. Okay, so I can represent them conveniently using this kind of a matrix. So you will see this a lot. So what I have written is there is person 1, person 2. Person 1 has 2 options, clean and don't clean. Person 2 has 2 options, clean and don't clean. And depending upon what they do, they have these 4 outcomes. And you might have some preference structure over this outcome. Okay, for example, this is one possible. So we will come to this in a moment. Okay, all right. So for example, I have written a preference structure which is more or less similar to what Sitavra was saying. That person 1 prefers. So when Sitavra said that he prefers O3, that's from the perspective of person 1, I guess. Okay, so as a person 1, you prefer O3, and so you have a structure like this. Okay, so the central question is, so person 1 has a preference structure, person 2 has a preference structure. What should they do? Okay, how do they go about achieving their preference structure? That ideally, for example, she would like to achieve this one, if not then this one, and so on. Okay, all right. Okay, so the usual way to do this, immediately what you do is that you represent this using numbers. Okay, now this is a big step actually. I mean that's not that trivial. We will talk about this. So for example, I can put some numbers representing them this preference structure. Okay, any numbers which will obey that preference structure. For example, here I have written 4, 2, and so on, and then I will have this kind of a structure. Okay, so question is this step from person 1 to this one, where I have represented this preference structure using numbers, is that quite, that's a big step actually. I don't know whether you, so what you assume is that my preferences have all the nice properties as these numbers. Okay, for example, the numbers are transitive. Okay, so transitive basically means that if I prefer A to B, okay, if I prefer A to B and then B to C, then I should prefer A to C. Okay, but human beings are notoriously very, very deficient in these kind of things, especially kids. Okay, I think the kind of the folklore example is about ice cream flavors. Okay, so for example, you might like vanilla compared to chocolate, chocolate compared to strawberry, but then the other way around. Okay, you prefer when you offer something. Okay, that's so choices may not be the options, the preferences may not be transitive for actual human beings. I don't know about animals. You can go and find out. Okay, and the other thing is that there's also something funny. For example, have you heard the story about one person going to a restaurant, let's say in Chennai, for breakfast, and then he asks, okay, what is there? Okay, then the waiter says that so we have only idli and dosha. It's too early in the morning. So then he said, okay, I will have idli. Okay, then the waiter goes to the kitchen and comes back and says that, sir, puri is also ready. So what do you want? Oh, puri is also ready. Okay, then I will have dosha. Now that's now this happens. The presence of a third option actually can change the preference structure among the two and so on. So these kind of nuances are there in actual world. And quick search, you will be convinced that there are a lot of interesting research still happening in this, not still, actually happening in these fields. I mean, I just randomly picked up a couple of papers, for example, identifying non-transitive preferences and whatever that is. These are recent papers from decent authors, I guess, but you can read about them. Okay. So usually, but then we don't worry about this stuff. But we will assume that you can represent your preferences using numbers, okay? Using numbers like what we do, okay? So this is the definition of a game. So a game involves players or agents or persons. Then there are some rules, there are some consequences, and depending upon that, the numbers which we call as payoffs, okay? So this is the structure of a game. So usually you will see this terminology used a lot, so I will just write it down. Okay. So game usually involves these components, okay? So the reason why I am writing this, because if you ever pick up something related to game theory, you will see this notation as a standard one across, okay? Okay. So a game has these components where generally I is the set of players, okay? Could be one player, does not happen, you need at least two, okay? So n is greater than 2, so the number of players. And this stuff Si is what is known as the set of strategies of player I. For example, in our case, person 1 has, let's say, S1, then his strategy set is clean or do not clean. It's a set basically. And S2 also has the same thing. So in this example, I is just has 2 elements, okay? And these combinations, when I choose clean and he choose clean and so on, so you will say that that's a strategy profile, which is the set S, which is the Cartesian product of all these n sets. So what do you mean by a Cartesian product? It is basically, so player 1 has 2 options C and D, player 2 has 2 options C and D, and then S is basically the set which are all possible combinations, okay? It could be CC, could be CD, could be DC, and it could be, it has 4 elements, okay? So it's called the strategy set. And each element of this is usually denoted by the small letter s, okay? S, it's an element of S, okay? Okay, so you have players, you have, each of them has strategies, and when each of them chooses a strategy, I can talk about a particular strategy profile, okay?
What is that symbol after?
Where is it? Oh, this one? This is a equal sign. Okay. Equal. Okay. Okay. Player strategies. O is the set of outcomes. Okay. Set of outcomes. So in this case, there are 4 outcomes: O1, O2, O3, O4. That's a set. And this sign basically represents for player 1 what is a preference structure over the outcomes, okay? for player 2, what is the preference structure, and if if O1 is greater than O2, it basically means that a preference is given to O1, and this sign basically means that they are equivalent and so. Okay. So O is the set of outcomes, and this is the preference structure, and basically f is some function which will map a particular element of S to some outcome basically. Okay. So for example, in this case, the outcome corresponding to me cleaning and the other person cleaning is basically O1. That's the structure. Okay. So you can see that these are the defining properties of the game, and if you replace this preference structure and this one with numbers, then we have, can I write here? So then we have the usual and then where this is simply the payoff of player I in strategy profile corresponding to S. Okay. So let's see in our example, for example, if I am player 1, my payoff corresponding to, let's say, take a particular element of the strategy profile, let's say CC. What is my number? My number is 2, and so on. So this simple pi is for the Greek P, payoff. So payoff of agent 1 corresponding to a particular strategy profile. Okay, so I hope this notation is clear. We are not going to use it anymore today, but we will be using it next time. Which ones? Oh yes, yes. It's not your problem. I mean, in the sense that you cannot do anything further than this is okay, but you cannot represent it using a pair.
What exactly is the strategy profile?
So it's basically any of, so if I choose C and he chooses C, that's its strategy profile, where each person has chosen something. Okay, yeah. No, all I'm saying is that if you have a structure which is transitive, I can use numbers to represent it. That's it. All right. Okay, so we are in this example where you have two options. So the question is then, what should or will persons 1 and 2 do? Okay. Okay. So given this, what will you do or what should you do? That is the question. So let's make some assumptions. So the usual ones are like, you should make your decisions simultaneously, no communications. Okay, players know this payoff table and so on. Okay, we can relax them, but for the moment, under these strict circumstances, then each agent would try to maximize this number because that was what your preference was, right? So because these numbers are written according to your preference, which essentially you want to maximize it. So how do you do that? That's the question, central question of games. Okay, so in this case, what will you do if you are person 1? Don't clean. Why?
Because if person 2 cleans or doesn't clean, my payoff's always higher if I don't clean.
Okay. Okay, that seems like a solid argument, and this is the argument. So what he's saying is that if I'm person 1, okay, let's see, okay, so these red numbers represent the payoff of me in any of the strategy profiles, and the green one correspond to this. So what he's saying is that you see, if I'm person 1, okay, no matter whether person 2 decided to clean or not, I will be better off by don't clean. Okay, because if person 2 decided to clean, then don't clean will give me a 4 instead of a 2, and if person 2 decided to don't clean the room, then I will get a 1 here instead of a 0 if I don't clean. Okay, right, which essentially means that I should not clean if I have that preference structure. Okay, so this is Sidavara's preference structure. You have a different one. We'll come to that. So, but person 2 will also argue in the same way. I mean, because this is kind of completely symmetric, but you can figure out, looking at person 2, that if whether person 1 cleans or not clean, the optimal thing to do is for him to do not clean. Okay, so one can say that the optimal thing to do in this case is actually for both of them, it's don't clean the room. Okay, yeah.
This person 1 knows the person 2 is smart. Now, if I know he's going to take the optimal decision, then I know he's going to take don't clean, then I would change mine to some other option because I know what option he's going to take.
Say that again.
So, let's say person 1 knows the person 2 is rational.
Okay.
So that means you know that he has done this argument something, he is going to take don't clean.
Yeah.
And so let's say that I know he's going to take don't clean because he's rational.
Yes.
So now I don't have to account for him taking clean.
Yeah, but even then, I mean, if he's not going to clean, then my best option is.
This game, the payoff is like this. But what
Yeah.
I'm saying is, wouldn't that lead to like a recursive argument? Like, say, I don't know if he's going to take this.
In some other game.
Yeah. So if I know that the other person knows that if I know that the other person is rational, then I know that he's going to take both these options and choose one, and that then I don't need to analyze both the options.
Yeah.
So
No, but it will always lead to. No, it won't lead to such recursive structure. We will see examples where we have a different payoff structure. I think you are referring to a different kind of payoff structure, right? Not this one. In this one, you can argue a lot, but let's see. Are there any other argument which will lead to person 1 cleaning the room? It's technically called as dominant strategy. Yeah. Oh, by the way, but me and Sidavara has written a couple of papers where we argue that there is a different way of seeing these things, but that's kind of not okay. So this idea that you employed, that he said dominant strategy and so on, that let's try to apply that. Okay, that's idea of strict and weak dominance. So what you essentially say is that the strategy don't clean strictly dominates clean. So strictly dominates means that for whatever person 2 chooses, I am better off by not cleaning the room, right? Okay. So these are standard terminologies. So strictly dominates basically means that 4 is higher than 2, 1 is greater than 0. So don't clean is strictly better than clean. Other way of saying is that clean is strictly dominated by do not clean. Okay. So these are kind of a standard terminology in game theory. So this is strict dominance. Okay. So what essentially you were arguing and him was saying is that it makes no sense to play strictly dominated strategies in a game. Okay, that's the basic argument of this. Okay. For example, let's try to identify this one. Let's take player. I have not written here, but it's player 1. I don't care about the payoff of the other person. So let's see this payoff structure, and can you identify, some strategies are strictly dominated by the other, some may be equivalent, and so on. Should be easy. Let's see. Compare A and D. Okay. So when I play A, I will get 3, 2, and 1, corresponding to E, F, and G. When I play D, I will get 2, 0, 0. But you see that A is strictly better than D, right? Okay. And there are other things, right? So I have written here A strictly dominates B. Okay. Are there other? Yes, A strictly dominates D also. A strictly dominates B, A strictly dominates D, and so on. C strictly dominates D. And also B weakly dominates D. What do I mean by that? So B and D, if you compare, this is 2, 1 and 0. This is 2. They are equal. 0 also equal. But at least for some column, I am doing better playing B compared to D. So that's a concept of a weak dominance. Okay. Okay. I'm as good as, so B is as good as D for most of the stuff, and better at least for one strategy. Okay. So you can employ this, A is equivalent to C and so on. So what you can simply do is that, since it does not make sense to play dominated strategies, you can just simply remove them. Okay. For example, okay, I don't want to consider B, I don't want to consider D and so on. Okay. But the problem is that that won't lead to a kind of a single strategy or anything like that. For example, if you apply that to this payoff table, then I will end up here. Okay. You cannot do anything further than this at this scale. Okay. All right. So the key idea of a kind of a solution of this kind of a situation is what is known as a Nash equilibrium. It's kind of an extension of what I said. The idea is that let's see this one. Okay. So there are these various strategy profiles, and we can say that a strategy profile is a Nash kind of equilibrium. Then no player can increase their payoff if others stick on to their equilibrium strategies. Okay. So we will talk about this in some detail. For example, in the last slide, I mean, this is not moving back. That's why I'm. So this is the end result of our strictly dominated strategy iteration, which we employed last time. And so you can see that in this payoff table, I can identify this, that is A and F and C and E, these two things as a Nash equilibrium. Okay. Why is that? Because if you see, if I choose A and the other person choose F, I get a 3. The other person get a 2. This is a Nash equilibrium because nobody can improve their payoff by changing from this strategy. Okay.
Wouldn't it be with respect to he doesn't have a incentive to move to other
Yeah.
So with respect to like every player is in Nash equilibrium with respect to.
No, I didn't get to what you said. So let's go through this. So this is a Nash equilibrium because if you are player 1, okay, can you improve your payoff by deviating from this one alone? That's important. Well, I can play E, but then I will get the same as this one. Can player 2 improve her payoff by deviating from this one? Okay, she can deviate. No, sorry, So you take player 1, she is getting 3 by playing A, and if I change to C, then I will get a 2. Okay. And if you are a player 2, then you are playing F. I don't gain anything by going to E. Okay. So this kind of a strategy profile is called as a Nash equilibrium, and you can see that there could be many of them in a game. Okay, there is no guarantee that, but in most of the games there will be many. Okay. Okay. So question, why you should play Nash strategies? That's a kind of slightly deep question. You can couch it in various ways. You can say that it's rational to play Nash strategies. We will see some arguments why you should play Nash strategies later. But the argument is that you cannot do anything better than unilaterally deviating from this kind of a profile does not improve your payoff. Okay, so it's like that. If everybody has chosen something like a Nash strategy, then I don't gain anything by deviating from that, and so it's a kind of struck state that we should play.
What I meant was bilaterally they can decide to move to.
Oh, there are. I mean, so if they can communicate and so on, but not always. We will see. There are additional things you can incorporate and so on. But this turns out to be a very key idea of analyzing games. And so we will see some very famous examples of two-person games. So, but before that, very quickly, how do you find this one, Nash equilibria in a game? So, if you have a payoff matrix like this, then so this is a sample payoff matrix where you are supposed to find the Nash equilibrium. It's basically a search problem, okay, from a computational perspective. Okay, so all you have to do is, if you are player 1, okay, if the other person is playing E, then my best response is what? A and B, because I am getting 4 playing A and B, 3 and 2 playing C and D. So I will just mark, these. Okay, and I do same with each column. Okay, if you are player 1, if the other person is playing F, then my best one is playing C. So, okay. And if it is G, if it is 3, and so on. Do the same for the other player. Okay, if I am player 2, then if the player 1 is playing A, then my best is 3, okay, corresponding to G, and in each row you can identify what is the best one. And if there is a Nash equilibrium, then that will be underlined, something like this. Okay, that's kind of a very.
It may not exist.
It may not exist in this case, yeah. And there could be multiple of them and so on. All sorts of things can happen. Yeah. Oh, identifying a Nash equilibrium is very easy. So if you have BE, can you, if you are player 1 and if you are player 2, put in the shoes of player 1, put in the shoes of player 2, can you improve your payoff by deviating from that? That's a basic question. So for example, if you are player 1, okay, can you improve your payoff by changing from B to some other strategy? Well, you will get equal when you play A, but then the other player will respond that with G and so on. Is that okay?
The Nash equilibrium is from the point of view of only one of the players.
No, both. This is strategy profile. Yeah?
Is BE the national equilibrium?
Yes, I suppose. I constructed 2 examples like that. Yeah. Yeah.
What's it when you if I was such a way that you destroy another player, it's like what?
Or you cannot unilaterally do that, right? I mean, how do you change the other person's payoff?
Of course, yes, change the
You can change the preference. I mean, if Siddhartha changes his preference, yeah, his room will be clean.
destroying other players.
Oh, that can happen. Yes. So it's kind of you are vindictive or something. I mean, you want to destroy the other person. Yeah.
If you destroy that, it's a payoff.
So it will be incorporated in your preference structure, for example. You will give the most weight to the outcome in which you destroy it, something like that. Okay. So what I wanted to say is that it's a search problem, and if you have several players and a lot of strategies, that's not going to be an a very straightforward thing. But in the end, it's a search problem, and then you can find out. If there is one, then you can find out. You can write an algorithm to find it out. Okay. So I will quickly go through one of the a few of the important two-person games. So can I take 15 minutes? Is that?
We started late.
Yeah. And we will play a game and we will figure out whether we are playing Nash equilibrium. So Shakti will talk about this in some detail, I guess, prisoner's dilemma. Okay. So there are some important two-persons game which kinds of forms the foundation for a lot of analysis in a lot of different fields, okay, economics, sociology, psychology, and so on. Okay. So one such thing is the prisoner's dilemma. The original story involves prisoners, but that will take a bit of deviation from stuff. This is, I think this is much better in the sense that, so imagine that there are 2 underground people who want to engage in a deal where, so there is a buyer and there is a seller. The seller want to sell diamonds and the buyer will pay him in cash. Okay. So it turns out that, of course, this is illegal. So you want to do it very quickly at some undisclosed location. You don't have time to check what is inside the bag. Okay, you just exchange the bag and then you go on. You are not going to meet, hopefully, further. Okay. So the thing is that if you are a buyer, then you have 2 options, right? Okay. What is the option? The option is that you can bring a suitcase full of cash. Okay. But you can also have the option of not bringing anything. Okay. Maybe you can just stuff it some trash paper and hand it over. Okay. If you are a seller, you also have that option, right? I mean, you can either put the actual diamond or maybe some fake diamond or empty box and so on. Okay. And if your preferences are just like in the room example, then the Nash equilibrium of this game is actually mutual defection. Okay. Why? Because if you are from a buyer's perspective, whether he brings actual diamond or not, I am better off by giving him a khali suitcase. Okay. So in this game, it's quite famous that there is only one Nash equilibrium, and that is this mutual defection, and it has been a very important game to study the evolution of cooperation. Okay. Why? Because if you see this, it's quite counterintuitive, right? I mean, if you live in hostels, of course you end up cleaning the room. It's not like you are not going to live in unclean situations. You have a different opinion. Okay. So Shakti will talk about why this is actually an important game in the evolutionary game perspective, especially in the evolution of cooperation. So people do cooperate. We know that we cooperate, irrespective of the fact that in several situations defection is the kind of best strategy in some way. Okay. Well, so one can go on describing that in some great detail. Why, for example, Prisoner's Dilemma is the game if you want to understand the evolution of human way of doing things. Okay, we're building large corporations where you need a lot of cooperation between agents and so on. Okay, so there's a great amount of literature, and I believe if you want to pick up one problem which is studied by scientists from diverse set of fields, I would suspect that Prisoner's Dilemma will be the top one. Okay, just to give you a hint, do you know Freeman Dyson? Freeman Dyson is a great physicist. So he has written a paper on Prisoner's Dilemma on the right page of 99 or something. He's dead now. 2015 he died. I think he wrote a paper. 2012 very famous paper in PNAS. So you can just about this basic structure. Okay, nothing else. Okay. All right. So what are the other games? So this is also about cooperation, and the story goes like that. So there is a tribe, okay, and they want to, they go for hunting, and they have the option of either to go for a stag, which is a bigger animal and which will feed a lot of people, or they can go for a hare, which is a smaller one, of course, and easy to catch. Okay, so the thing is that you need cooperation from the other person to catch a stag. Okay, but you can catch a hare alone. Okay, there is no problem. So one can make an elaborate story out of it, and I don't want to go into that. But the point is that this is the kind of payoff structure which is representative of this situation. Okay, if both of you go for a stag, then you are very happy. You will get a payoff of 4 and 4. But there is always a possibility that one person think that okay, that's too dangerous, and there is an immediate benefit in going for a hare because I can do that alone. I don't need the cooperation. I don't need to trust the other guy and so on. So they have this. So this payoff structure basically represents this. If I go for stag and he go for stag, I will get a 4. He will get a 4. But if I go for a stag and he go for a hare, he will get the hare, 2 marks. I am going for the stag alone, and I will end up with 0. Okay, and it's symmetric about the other player. So can you identify quickly what are the Nash equilibrium in these games? Okay, equilibria. Yeah.
Why not 2, 2,
Okay. So this depends upon the version of the story. I think here is that you are going to share it because you are going for hare together. Okay, this is you are catching alone, so you keep the catch yourself. Okay, so quickly, what are the Nash equilibria? 4, 4 and 1, 1. Huh? These are the Nash equilibria. So that's known as a coordination problem, and in some literature, this is again projected as the problem to understand the evolution of cooperation in human context, because all of our progress is due to the fact that we are going for stag alone, stag together, and bigger projects, for example, and so on. Okay.
When Rousseau talks about this in social contract,
Yeah.
I think this was the oldest game.
Yeah. So he says that this is the game, not the prisoner's dilemma. You should study to understand the problem of cooperation. Okay. All right. Evolution of cooperation. It's basically a coordination problem. Okay.
They mutually decide before.
No. So in these ones, there is no communication beforehand, nothing. You just have to make your decision simultaneously. Okay. So I am just describing the Nash equilibrium. Now there is, you can go on, for example, discussing why, for example, people will choose this one over this one and so on. For example, communication is a factor and risk dominance is there. I mean, there are other concepts, but let's not go. It will be standard. Yeah. Okay. So this is one interesting one, the battle of sexes. So the story is again that so let's say that me and my wife in the morning we are going to our office, and so in the evening we have some plan. Okay. So I want to go for a cricket match. Okay, and wife wants to go for shopping. Okay. So we have an argument, and then we have no time to settle down, and then on the way to office we'll say I will shout cricket match, and she will say shopping. We'll see you in the evening. Not decided. We will part our ways, and in the in the evening, okay, there is no communication. We have to go and find out whether the other person is there. Okay. So the thing is that I prefer cricket, obviously, and I also prefer company, and she also has. Okay. So there is obvious what is that, gender undertones. I hope this is not politically correct. It's recorded, right? I mean, I'll be in trouble. But it's called Battle of Sexes for a reason. Okay. But I have seen that in modern versions they carefully avoid the gender reference. Okay. Anyway, so what happens? So if both of us go for cricket, then I am extremely happy. Okay. She is. I don't know what this smiley means. It is intended to be kind of. I don't know what do you mean by this one? It's a smile. A kind of smile.
I'll get you later.
Yeah, that kind of. Yeah. And if I go for cricket, and she go for shopping, okay, so we don't have the company of each other, and we are kind of unhappy, both of us. Okay. And if I go for shopping and she go for cricket, that will be the worst. Okay, that's like I came for you and you were not there. Huh? So this is like the worst. And this one is the opposite of this one. We both of them went for shopping. She's happy. I'm kind of happy too. Okay. So the payoff will looks like this. Again, so what are the Nash equilibria in this case? This is again a coordination problem, and you can easily identify that these are the Nash equilibriums. Okay, cricket, and shopping. So it's again a kind of coordination problem. How do coordinate? And somebody mentioned that one possible way of coordination is by introducing communication. Okay, that's obvious. Okay, so last one is the famous hawk dove or chicken or snowdrift, extremely important from in the field of evolutionary biology. Again, the story is obvious from the figure that you have the option of, I think this is casted in the form of cooperation between nations. Okay, so cooperation basically means that you can trade and peacefully live together. So cooperate is basically means that trade and no problem. Defect basically means that you basically nuke the other guy. Okay, that's basically defection. So in the social science context, it basically means aggressive or peaceful personalities. And if some of you are from psychology, then you will see this a lot. Okay, if some person is very aggressive, then the other person will be peaceful, relatively. Okay, so again, it's best. So what is the best outcome if you are nation A? Okay, if you are nation A, the best is actually to nuke the other guy and the other guy cooperate. That doesn't sound very, but nuke basically means that you are the kind of aggressor and you get a lot of things. Okay. All right. So this is the payoff structure represent. So nothing sacred about these numbers. Okay. All that matters is actually the relative ordering of them. Again, can you identify the Nash equilibria in this case? So this is an anti-coordination game where the Nash equilibria are this one. Okay. If person 1 is defecting, aggressive, then it's better for me, person 2, to be cooperative. This is a Nash equilibrium. Why? Because you see that, well, by definition, it's a Nash equilibrium. I don't get anything. If I'm person 2, I don't get anything by going away from this, and this person also does not get anything by going away from this one. Okay. Okay. Again, it's a question of anti-coordination, whether person 1 is going to be the aggressor or person 2 is going to be the aggressor. So it has several names. The name chicken and snowdrift comes from some other context. Chicken basically means that you and the other person is actually driving towards each other very fast, and then if you swerve, you are a chicken. Okay, you are the a loser in some sense. So who will swerve? That's a question. If neither swerves, then this happens. Okay. All right. Okay, so we will see this game again later. Okay. Finally, a quick example where you don't have a Nash equilibrium. You can see that this is a problem where you don't have a Nash equilibrium. So this game is simple, that I am person 1. I will either say heads or I will say tails. You should also do that simultaneously. And if our things match, then I win. Okay. Head, head, I win. Tail, tail, also I win. If I am person 1, and otherwise person 2 will be. So here you can see that by the definition of whatever we had, we don't have a Nash equilibrium. Okay, but we will learn later that we do have a Nash equilibrium in what is known as mixed strategies, or when I have the option to randomly select between heads and tails. Okay, okay. So this is what about finding Nash equilibria, a search problem. Better to perform the iterated deletion of strictly dominant strategies first, and then it's kind of search problem. So final question: do people actually play Nash strategies? What is your opinion? Yeah. Okay. Let's find out. Let's find out. Okay. So I'm going to, in the true fashion of game theory, I have a game in my bag. I have. No, this is not what you think. This is to entice you. Okay, just give me a second. Well, what do you like? This one. This is like the. Okay. Okay. Question number 1. Which one do you like? This one or this one? Which one do you prefer to have? Cadbury's or candy? Candy? Cadbury? Okay, fine, I will give you. Okay. But before we begin, I need your cooperation. Don't talk to your neighbors. You should not see what the other person is doing. Okay. You should be all like John Nash. So, promise? No. No, you are not promising. So let's take a pledge. Raise your hands. Raise your hands. Okay. And repeat after me. In the name of John Nash. Okay. I will not collude with my neighbors. Okay. I will be selfish. And I will be rational. Whatever that means. So you have to repeat that. Okay. So this is the game. Okay. I'll give all of you candy, or okay. Don't look at your neighbors. You have to write Cadbury or candy on your paper, and if 5 or less persons write Cadbury, okay, I will grant everybody's wish. Okay, meaning that those who wrote Cadbury will get Cadbury and the rest will get candy. If more than that, I will keep the chocolates. Fine. 1, 2, 3. Okay, right. And don't look at your neighbors, close your eyes, okay, close your eyes. And whoever wrote Cadbury, please raise your hands. Oh, I get to keep the chocolates. Huh? 1, 2, 3, 4, 5. Oh, now you can open your eyes and see who has. No, don't change your options, okay? Okay, nobody gets it, okay? I get to keep. Once more, okay? Write that again. Once more, I am giving you a chance one more time. Quickly down your neighbors, I hope you have written, and then close your eyes. And Cadbury, raise your hands. Close your. Oh God. In the game theory fashion, this is called suckers. I don't know. Okay. Do you want one more chance? You want? Okay. Maybe I will give who is a fantastic speaker. You're emotionally. I mean, can you arouse these people to? Can you give a speech and make them take the candy? 1 minute.
In the name of John nationally, everybody, for the benefit of all, right? Candy.
Okay, then I will get to keep the chocolates. That's very good. Yeah. One more. Okay, write it. No, don't change. Don't cheat. Close your eyes. Raise your hands. Chocolates. No, you're okay. So 1, 2, 3, 4, 5, 6. Okay, you don't. You don't win. Okay, question. Final question. What is the Nash equilibrium in this game? Or what are the Nash equilibria in this game? Let's quickly find it out. What are the Nash equilibria? Do you know? How do you? So this I wanted to do because it's a multiplayer game with a lot of strategies, and so you will get a taste of how to do this. Let's quickly do this. So what are the Nash equilibria of this game? Can you identify very quickly? Everybody getting candy, yeah? Okay. Everybody getting candy is that a Nash equilibrium? 5 getting candy, very good. Okay, Cadbury, so not candy, Cadbury 5 and all the remaining. This is a Nash equilibrium, right? So what about the other ones, okay? So Cadbury, suppose 7 or more choose for Cadbury, okay? This is what you have done. Nobody gets, but is that a Nash equilibrium? That's the question. What is the definition of Nash? Think about whether a person benefits by deviating from that strategy. So if 7 or more has chosen Cadbury, then if you are a Cadbury person, do you gain anything by deviating from to candy? No, you are not going to get anything. What about candy? No. So this is a Nash equilibrium. Okay. You can also verify that 6 is a bit dicey, but Cadbury 6, exactly 6, and all the remaining. This is also not a Nash equilibrium. And I hope we covered all the cases. Oh, less than 5, okay. Cadbury less than 5, okay, less than 5. And all the remaining people can. Is this a Nash equilibrium? Suppose only 3 people choose Cadbury. No. Why? Because a candy person could have unilaterally deviated and then played. Okay. So you were stuck at this Nash equilibrium. I can make this. This is a very difficult problem to solve, right? I mean, if you really want to get the chocolates, that's slightly difficult. But actually, I wanted to give chocolate. No, I am in a dilemma. So
they'll have to wait for the next class.
Maybe yes, because I had more chocolates, but then you know what happened. My daughter asked me, what are we going to do with this? And I tried to explain the game. And she patiently listened and then, can you do it with 1 less chocolate? So I had 7, okay. That's a rational question, okay. Of course, I have to say yes.
You should have told us you'll get them anyway.
Can't you do it with 1 less? Yeah. Sorry, sir.
You should have told us you'll get them anyways.
Yes, but I didn't know that. You were so. Okay. So 7 started with 7. It became 6. And then yesterday night, I asked the same question myself. Can't I do it with one less? So turns out that I can actually do it with just one chocolate. But I don't want to look very cheap. So anyway, I mean,
But if you keep doing this and in the last year also they can't do it, maybe all of them will go back.
yeah, that's also very bad. Okay, so let's finish off this session with saying why would one play Nash strategies? Okay, what is so great about it? You can put it in various words. The one thing is that no regret. Okay, no regret. For example, you see here, if only one person has chosen Cadbury and all the remaining candy, okay, then somebody might have a regret. Oh, I could have chosen. Okay, it's like that. So at Nash equilibrium, there is no regret for a person. After knowing the result, he won't think that, oh, I could have chosen differently. Okay. The second thing is that it's a self-enforcing agreement. Okay. For example, if I declare that I'm going to play this and you declare that you are going to play that, at Nash equilibrium, that is a self-enforcing. You don't need any contract. You don't need any communication. Okay. Because it's self-enforcing. Because nobody gets to deviate from that. Nobody gets to benefit from that. Another way of saying that it's a viable recommendation. For example, I am an external thing. You are playing the game. I can recommend that you do this, you do that, and then that will happen by itself. Rationality with correct beliefs is a slightly more involved stuff, but then we don't have to worry about that. So homework in the true style of game theory. Okay. So tomorrow when you come at 9. Okay, tomorrow when you come at 9, I am going to ask a few of you to summarize what we have learned today, but not just in this class.
You could also use this.
So what did I say? Tomorrow when you come back, I am going to ask a few of you to summarize what you have learned today, not just in game theory, but the entire session today. Okay, I am going to ask, or maybe I am not going to ask. Okay, so I have two options. Okay, so this is me. Ask, do not ask. Why? Because if I ask, then I have to listen to that patiently for a few minutes, and then time will go, and then I will get delayed. I might ask because I want you to also remember what I. Okay, now you have also two options. You can either prepare, okay, or no, don't prepare, not prepare. Because your homework is actually what? You try to figure out the preferences of each person and then figure out the Nash equilibria. And if it, it's optimal for you to prepare, prepare. Otherwise, come and you might face the question. Okay? You got the homework? Okay, then see you tomorrow. Yeah. You can take these chocolates. I don't think I have. Who wants?
You can wait for the next time.
Or maybe I'll wait. Yeah, that's better. Okay.
Let's see on the third day if the knowledge.
Yeah. So we'll play this again. We will play this again. Okay. Try. You can communicate with yourself. Now you are free to do whatever you want. Okay. You can make the other person, all sorts of agreements. Okay.
Will you make random?
Tomorrow. Of course, I have to. Assuming that I have a good random number generator in my brain. Okay, I'm going to pick you. No. Okay. All right. So you can discuss among yourself. You can share. There are 5 of these. Okay. No more. But remember that I can do it with one less. Always. Okay. Yeah.